Here, I want to look at the relationship between the row space of a matrix and the null space of a matrix. And it turns out there's a similar relationship between the column space of a matrix and its left null space. And the relationship between these pairs of subspaces is that they are orthogonal complements of one another. What do I mean by that? Well, let's first start with the first pair that I mentioned, the row space and the null space. Okay? Let's suppose R is some vector in the row space, which remember we denote as the column space of A transpose. And I should start by assuming that A is some arbitrary n by d matrix. Okay, R is in the row space of A, and let's suppose n is in the null space of A. It turns out that R and n are orthogonal. And all I've assumed is that R is just something in the row space and n is something in the null space. How do I show that they're orthogonal? Well, the key here is learning how to precisely state in an equation what it means for R to be in the column space and n to be in the null space. I'll give these conditions numbers. I'll start with the first one. What does it mean that R is in the column space of A transpose? What this means is that R is a linear combination of A's rows, because it's in the row space, or equivalently of AT's columns. What this means is that R is an output when you multiply A transpose by something. And that something can be some other vector. Okay, where here y is just some vector in R. What would the dimensions have to be? Well, A transpose is d by n, which means to multiply A transpose by a vector, it must have n things in it. So R is just some vector in Rn. So the fact that y is some vector in Rn. So the fact that R is in the row space just means that there is some vector y such that ATY gives you back R. R is a possible thing you can make by doing A transpose some other vector. So that's very good. 2, what does it mean for n to be in the null space of A? What this means is that when you multiply A by n, you get back the 0 vector. Okay? Now it turns out A and R, sorry, not A and R, n and R are orthogonal, like I said, and the question is, how do we show that that is the case? I'll give you a second to pause the video and think about it. Well, what I can start by doing is just computing their dot product and seeing what it ends up being, right? It's going to be something, it just may or may not be 0. Let's start. N dotted with R. I can take this somewhere because I know that R is A transpose Y. Perfectly legal dot product. Now, what I'll employ here is the fact that I know that the dot product can also be written as the transpose of the first vector times the second. And the order here doesn't matter. So U dot V is the same as U transpose V, same as V transpose U, same as V dot U. How can I employ that here? Well, I can use it to turn this expression into M transpose A transpose Y. Notice the dot has dropped now. Now what do I notice here? I notice that this looks a lot like using the rule that AB transpose is B transpose A transpose. This looks a lot like AN transpose Y. But fortunately, I already know something about n. I know that A times n is the 0 vector. So now I'm computing just the dot product of the 0 vector with y, and the dot product of any vector with the 0 vector is just 0. So just with these two expressions, I know that n and r are orthogonal. But what defined n and r? All that I assumed about n is just that it's some vector in the null space of A. And all that I assumed about r is that it's some vector in the row space of A. What this means is any vector in the row space is orthogonal to any vector in the null space. And so what this means is that the column space of A transpose, that is the row space, and the null space of A are what are called orthogonal complements. Any vector in here is orthogonal to every vector here. So everything here is orthogonal to everything here. And if you look back at, I want to say chapter 4.3, there's a cool picture of what it would look like for two subspaces to be orthogonal complements to one another. If we're thinking in R3, orthogonal complements may look like a plane, that could be one of the subspaces, and the other one could be a line that is orthogonal to the plane. That's a bad orthogonal symbol. But this is the picture I want you to have in your mind. One of these could be the column space of A transpose, i.e. the row space of A, and the other could be the null space of A. This is the relationship they would have. Any vector on one is orthogonal to every vector in the other. So the column space of A transpose and the null space of A are orthogonal complements. And as a quick refresher, these are both subspaces of R what? We should always think when we're dealing with a subspace, what is this a subspace of? What universe do these vectors live in? Remember, the row space, it is made up of the set of all linear combinations of the rows of A. And the rows of A, how many things do they have in them? Well, A has n rows and d columns, so each row has d things in it. Okay, which means the things in the row space are in Rd, and the things in the null space are made up of vectors that it is legal to multiply A by, right? The defining characteristic of n here was that an was the zero vector, but that meant it had to be possible to multiply A by n. And how do the dimensions need to work? Well, if A is n by d, sorry, I'm using n twice here. This is n as in the number, this is n as in the vector. Then this vector n had to be d by 1. So things in the null space are also in Rd, which is why we were able to take their dot product in the first place, right? You need to ensure the vectors you're working with live in the same universe, i.e. have the same number of components before you can dot them in the first place. So the row space and the null space, both are subspaces of Rd, and what we've shown now is that they are orthogonal complements to one another. Anything here is orthogonal to everything here, and vice versa. Now these are not the only orthogonal complement relationship that exists with regards to these subspaces we've introduced in chapter 5.4. There's another pair of orthogonal complements, like I stated at the start of the video, and that comes from looking at the column space of A and what is called the left null space, i.e. the null space of A transpose. It turns out these are orthogonal complements too. Can we prove it? Again, I will give you a second to pause to see if you can work out the steps on your own. Here's how we'll do it. We'll again start by assuming that, I don't know, C is a vector in the column space of A, and N is a vector in the null space of A transpose. And just from these facts, I'm going to need to show that C and N are orthogonal. Again, part of the challenge is in precisely stating what it means for C to be in the column space. Remember, C being in the column space, all that means is that it is a linear combination of A's columns. Or in other words, there exists some x in Rd such that C equals AX. That's all it means for C to be in the column space. What does it mean for, and I'll just, so we're super clear here, C lives in Rn. What does it mean for n to be in the null space of A transpose? All that means is if you take A transpose and multiply it by this vector n, which has n things in it, again, that's a little confusing, but what you get back is a zero vector. Okay, so this vector here lives in Rn, and so does this one. So it's valid to consider what would happen if you took the dot product of them both. Okay, and when we do that, let's see what happens. We take the dot product of C and N, but remember C is just AX. We're dotting that with n. Now somehow I'm going to need to use the fact that A transpose n is equal to the 0 vector. Then I can again employ the equivalent way of writing the dot product as AX transpose n. Then distribute this, or distribute the transpose operator within the parentheses. So this gives me X transpose, A transpose n, and there we have that 0 vector once again. So this is X transpose the 0 vector, which gives me 0, the scalar. Okay, so once again, all I assumed was that C was just something arbitrary in the column space. I didn't assume anything more about it than that. And that n was something in the left null space, that is the null space of A transpose. And just with those facts, I can show that C and n must be orthogonal. And so, to conclude, what have we really shown in this video? What we've shown are two pairs of orthogonal complements. So the first pair we saw was that the column space of A transpose, i.e. the row space, and the null space of A are orthogonal complements. And we've also shown that the column space of A and the null space of A transpose, and again this had the English name of the left null space, are orthogonal complements as well. So that's what we've shown in this video, that there's this nice pair of relationships in these four fundamental subspaces, as some may call it, that we've looked at in this chapter. And just as one final reminder, both of these, and maybe I'll put this in a different color, both of these two subspaces, that is the column space and the null space of A transpose, are subspaces of Rn, while both the row space and the null space are subspaces of Rd. Which is why it was valid to consider the dot product of something in the row space and something in the null space in the first place. They're compatible vectors because they live in the same universe. In general, it's not possible to ask, are vectors in the null space and the column space orthogonal? Well, in general, unless your matrix is square, you can't ask that, because things in the null space have D components and things in the column space have N components. So make sure to keep track of the dimensions and shapes that you're working with when working on these abstract questions. But that's it. We've shown these two pairs of orthogonal complement relationships, and let us know if you have any questions.